Saul Perlmutter, Professor Adam Rees, and Professor Brian Schmidt, the Shaw Laureates in Astronomy 2006. May I first call upon Professor P.C. Chang, Pro Vice Chancellor and Head of Shaw College, to deliver the welcoming address. Professor Chang, please.
Professor Perlmutter, Professor Rees, Professor Smith, Professor Lau, Professor Chu, distinguished guests, colleagues, ladies and gentlemen, good afternoon. The presentation ceremony for the Shaw Prize 2006 was held last night in the Hong Kong Convention and Exhibition Center. As you all know, the Shaw Prize was established under the auspices of Mr. Run Run Shaw in November 2002 to honor individuals who have achieved significant breakthroughs in academic and scientific research and applications in the areas of astronomy, mathematical sciences, and life science and medicine, and whose work has resulted in a profound impact on mankind. The 2006 Shaw Prize in Astronomy was awarded jointly to Professor Saul Perlmutter, Professor Adam Rees, and Professor Brian Schmidt for discovering that the expansion rate of the universe is accelerating, implying in the simplest interpretation that energy density of space is non-vanishing even in the absence of any matter and radiation. For many of us sitting here as laymen in astronomy, I guess the citation might not be that easily understood. But one might still be interested to know how fast the universe can expand. What is the impact to us? Is there anything to do with Pluto being demoted to the status of a dwarf planet? Today we have the honor to have Professor Perlmutter, Professor Rees, and Professor Smith, the Shaw Prize laureates in Astronomy 2006, to deliver the Shaw Prize lecture on dark energy and the accelerating universe, past, present, and future. I'm sure they will enlighten us with many interesting findings of their study. We are most privileged to be able to host the third Shaw Prize lecture in astronomy at Shaw College. This has a special meaning to us, not only because the Shaw Prize and Shaw College have a common benefactor, but we are exceptionally delighted to witness the naissance of the Shaw Prize since the initial planning was carried out at Shaw College some years ago, and the announcement of the establishment of the Shaw Prize was actually held in this auditorium. We are grateful to Mr. Run Run Shaw for his generosity and the particular concern for youth education that made possible the formation of Shaw College at the Chinese University of Hong Kong. And at the same time, we have the highest regards for his dedication and passion in the promotion of scientific achievement that made the creation of Shaw Prize feasible. Without further ado, may I invite Professor Zhu Mingzhong from our Department of Physics to introduce the laureates and to moderate the Q&A section after the lecture. Thank you. Professor Zhu.
Good afternoon. It's my great honor to introduce our speakers today, especially because they are my heroes. Contrary to many of you might have thought, science is much more interesting when we find that we're wrong. And my heroes here today proved to the world that almost everybody was wrong when it comes to cosmology. The discovery was really one of the most important ones in recent years. So I'll introduce the speakers one by one. And the first speaker is Professor Saul Perlmutter, Professor in Physics of University of California, Berkeley. Saul graduated from Harvard University in 1981, and then he got his PhD from University of California, Berkeley in 1986. I got his CV and I looked down the list of all the honors and awards he got, and I got really jealous. So I won't tell you all about those. I'll just pick a few. He got the E.O. Lawrence Award of the U.S. Department of Energy in 2002. He was elected the California Scientist of the Year Award 2003. And then, of course, this year, he got the Shaw Prize in Astronomy, and also the International Antonio Feltrinelli Prize. I'm sure I got the pronunciation wrong, but you probably don't know anyway. So I won't take too much time. Let's just welcome Professor Perlmutter.
Well, good afternoon, and it's really a pleasure to be here. I thank you very much for having us for these lectures. I will be giving the first of the three talks on the topics of dark energy and the accelerating universe, and I will try to give you a little bit of the detail of what happened at the very beginning that brought us into this work, all three of us, in terms of what kinds of work we ended up doing, and then I'll pass some of the topics on to Brian and Adam after myself, so I won't be doing it, we won't all three of us be doing the same things three times. Let me begin by just commenting that the work that we're describing is, I think, the sort of work that you come into because you're asking questions which are some of the most fundamental questions that human beings, I think, find themselves asking. You walk outside and look at the sky at night and you find yourself wondering, does it go on forever infinitely, and will it last forever in time? And for basically most of human history, this sort of question was a truly philosophical question, and it wasn't until just the 20th century that we began to have a scientific version of this question, and this is partly because Einstein's theory of general relativity gave us some new conceptual tools to make it possible to talk about this sort of topic, but also because Hubble then measured an expansion of the universe, which meant that we started to see in more concrete terms what we could mean by the fate of the universe. For example, the question would be, well, he started realizing that we don't live in a universe that's standing still, but rather it's getting larger. All the distances between the galaxies are growing with time. And of course, you can immediately start asking yourself, will they continue to grow at the same speed with time, or might they slow down, for example, because gravity would attract all stuff to all other stuff in the universe? And then you might expect it to be slowing. In fact, you might wonder if it could be slowing enough so that someday it could come to a halt and then collapse into the end of a big crunch. And so that could be an end of the universe. So this was a question which I think even in the, well, you can start realizing that you can address about the future of the universe by looking into the past of the universe and looking to see what was happening back billions of years ago and how much the universe was slowing down back then. And if it was slowing enough back then, you could predict that it will slow enough to collapse in the future. This was understood even back in the 1930s, just the following decade after Hubble's discovery, by people like Bada and Zwicky, who were studying supernova, and they started realizing that in principle you could use a very, very bright exploding star, a supernova, to perhaps answer this question. And I'll show you why that would be possible. You could take the brightness of a supernova as an indicator of how far away it is. So the fainter it is, then the further away it is from us, and hence light has taken more time to reach us. So you're looking further and further back in time. And you could use the color of the spectral features of a supernova. So a supernova might look blue if you saw it nearby, but by the time you see it very far away, it looks red. And how red it gets tells you how much the universe has stretched because while the light is traveling to us, it stretches by the exact same proportion that as the wavelength stretches, by the same proportion as the universe stretches. So it's a very direct way of plotting how much the universe is stretched as a function of time, and in principle you could go back and look to see which of these lines of deceleration we live on and make a prediction of what will happen in the future. And this could be done then with supernova, but the problem was, and Bada wrote about this back in the 30s, the problem was that the supernova that they knew of at that time weren't quite good enough standard candles. They weren't all quite the same brightness. They varied by more than a factor of 2 or 3 in brightness from each other. And so it looked like a good idea, but it wasn't really practical to do. And basically that's where the problem stood for maybe the next half a century, next 50 years, until 2 things happened in the mid-1980s which got me interested in it, and I think others that you'll be hearing from today. And those 2 things were the following. First, there was the realization that the supernova could be subdivided into subclassifications, and it was in the mid-80s that the type 1a subclassification began to be made, and by these are some of the papers that were discussing it, and it was with this realization that we were able to start seeing that this one subclassification really was a much better standard candle than the others. For example, the paper by Panagia showed a histogram of supernova brightnesses, and you can see that those supernova found in spiral galaxies have a very big variation in brightness, but those found in elliptical galaxies look like they're actually rather tightly dispersed, and the interpretation was that this might be the subclassification that is a better standard candle, and also that the spirals are known to have dust, whereas the ellipticals aren't, and so these might be a mix of different subclassifications and some dust make a range of brightnesses. But this was quite suggestive that we see perhaps a subtype which could be a good standard candle, and that looks like it was a very promising route to go back to the original ideas of Bada and Zwicky. Now, the other development that came in the mid-1980s was the development of the new sensors, the CCD detectors, which are like the detectors that we use in the back of our camcorders and digital cameras today that most of you have. Those just became available in that period, and we, in the beginning of the 80s, started to first use them for astronomy. And in fact, I was involved in a project that was one of the first projects to use this, and to use the new computers that were just becoming fast enough to analyze the data that came out of these detectors. So I worked on a project that was run by my thesis advisor, Richard Muller, which was doing a nearby search for supernova using a small robotic telescope and automatic detection of the supernova by the computers. And so I worked on the software that made it possible to subtract a galaxy from supernova plus the galaxy and just find the supernova. And that led to a automatic searching technique that we found, we were up to our 20s when that project stopped. And here was an example from back in 1986, one of the earlier ones, of a supernova clearly seen that wasn't there before. So these 2 developments led Carl Pennypacker and myself, who were both postdocs in Richard Muller's group in 1987, to decide to try out the original idea of Bada and Zwicky of measuring the deceleration using the supernova. And so we began that project, and it looked very promising, but we were aware that it was not going to be easy. And there were a number of reasons that we knew that there was a lot of work to be done to make this possible, and that when we proposed it, we did not get an immediately enthusiastic response from the referees and the reviewers. And those were some practical problems of actually trying to find the supernova. There were some specific technical problems of how you actually analyze those very, very faint supernova and compare them to nearby examples. And then there were issues about the standardness of the supernova themselves and their consistency over time that had to be addressed. And so these were the specific details that we saw as the hurdles that had to be accomplished, gotten over in order to do the project. So I thought I would tell you today, in my part of these lectures, a little bit about how we addressed these problems, because what's interesting about this particular measurement is that it's so simple. It's one of the simplest, very fundamental questions that I know that you can address. that you can actually look to see what the specifics are of what it would take to make the measurement, and I think most people here would understand what it would take to do this particular project. So I think it's interesting to follow that level of detail, and I'll try and just do that relatively briefly to give you a sense of the texture of what it was that we were doing when we started the project off. So first of all, the question of can you find these supernovae at all? And can you find them far enough? Can you find enough of them? Can they be found early enough so that they can brighten and then fade away and you can measure the peak brightness? The peak brightness is what we knew was standard. We couldn't use them if we found them months after they had already peaked. And that was, these were fairly difficult problems because the supernova, if you had to choose a research tool, you would never choose a supernova. It's a real pain in the neck to do research with it. They're rare, they only explode a couple of times per millennium, they're random, they don't tell you when they're going to go off, they only, they rise and they fade away, they don't stick around for you to study them. They're just terrible to do research with. And in fact, at the beginning when we started this project, there had been one other project that was begun just a little before us. We didn't know, but within a year or so we had seen these results, which is that a project led by a Danish team, led by Norgard Nielsen, searched for several years, for this type 1a supernova, and in the end they managed to only find one type 1a, and it was several weeks after it had already done its peak. So the critics of our project said that, look, this does not look like a very viable job, and so this was the first concern. Now, the approach that we took to this was to, instead of looking at one galaxy at a time for supernova and wait, 500 years, and this is essentially what you do for the nearby ones. You go from one galaxy to another galaxy to another galaxy. And instead of doing what the Danish group did, which was look at a small cluster of galaxies, we decided to build a wide field camera that could allow us to look at 10 times as many or 20 times as many galaxies as you could see even in a cluster of galaxies in every shot and every time you open and close the shutter of your camera. And we had to develop this very unusual optical system that would bring light from a very big field onto a small CCD detector. So it was one of the unusual systems. This is a coin, just to give you a sense of scale here. And this thing went onto the Anglo-Australian telescope, the 4-meter telescope, and that meant we were able to work with a large enough telescope with a wide enough field of view to be able to search at great distances, but be able to see through hundreds and thousands of galaxies all at one time. Now, you got images like this from the AAT, and you can see all these little galaxies that we were searching for supernova in, and you would then take an image another time in the year, and you would subtract it from the first one, and you'd be left with, if you lined it up right, just the spot that got bright, and that's your supernova. Of course, we did this in software, so we had to go back to our image analysis software and develop that much further. So here's what the computer did, and it leaves you with just the supernova there. So that seemed to work, but the remaining problems were still haunting us, because you could find the supernova, but then you couldn't prove that you had a supernova because you need to schedule the largest telescopes in the world to get a spectrum of it, to identify the supernova, and then you need to schedule the largest telescopes in the world to follow it as it brightens and fades away, and no telescope time assignment committee would give you the time to schedule a telescope 6 months in advance for a supernova that may or may not appear on that March the 3rd that you're proposing for time. So we had to figure out a way to make the whole operation more systematic, and what we came up with was I developed this new search strategy, which ended up, I think, making this possible. Here's a timeline of new moon to full moon to new moon, and I realized that if you collect all of your first images just after new moon, wait 2.5 weeks or so, and collect all of the second set of images just before the next new moon, and now subtract these from these and look for the supernova that's bright that wasn't there before. Now you can, first of all, look through enough galaxies at a time using this big wide field imager that you can guarantee not just one supernova, but half a dozen or more supernova. And so once you get up to a statistically significant sample of supernova, then you can be sure that you always have something to observe on this date. Now, the other advantage is that with this short time scale, that you can guarantee that the supernova won't have enough time to reach maximum and then fade away. And they rise in a couple of weeks and they fade in a few months, but this way you always catch it while it's still on the rise. And so that way you could guarantee that on this particular date, right before a new moon, which is the time that you need to do the spectroscopy, you will have the supernova and they will still be on the rise and you will have more than one. And so now you can schedule the follow-up photometry on the nights afterwards and the spectroscopy. Once we demonstrated this, we were able to start applying for telescope time, and finally apply for time at the telescopes that you really want to use for this in Chile, where the weather is good enough that you can guarantee that you'll be able to do this whole sequence without getting hit by clouds and rain. Now, the first time that we did this batch observation, we called up the International Astronomical Union telegram service, which notifies astronomers around the world when a new supernova is discovered, and we warned them ahead of time that we'll be sending them a half a dozen supernova discoveries in 2 weeks from now. And they laughed because nobody had ever predicted a supernova discovery before, and certainly nobody had ever found more than one at a time before. And here we were saying that we're going to find half a dozen, and it'll be in 2 weeks from now. And of course, it sounded unusual, but in fact, we then sent out these telegrams semester after semester for the following years, and as this batch technique, as we called it, worked. We produced batches of supernova. I think the first one was not half a dozen. I think the first one was actually more like 8 or 9 in the first telegram. So this did work, and we had gotten through this problem of finding the supernova and making them a systematic tool. The next problem was that even if you found the supernova, there's the question of could you identify that they were the subtype, these type 1As? And it wasn't clear they'd be bright enough to actually get a reasonable spectrum of them. So in fact, the first spectra that you saw, this is actually a later one, it's even better, but the first ones really just looked like a lot of noise. And even people who had worked with supernova before said to us, well, that doesn't really look like a supernova. But we started to realize that you could take advantage of the fact that supernova features are very broad spectral features. They aren't on this very sharp wavelength scale, like the features of a galaxy would be. And that's because an explosion spreads all the features out. And that meant that we could actually afford to cut out these sharp lines and then smooth the whole spectrum to look something like this. And now you begin to start seeing the broad features that look like the supernova. And the red line there shows you what a template supernova spectrum looks like, redshifted to match that particular high redshift position. And you can see that now you could recognize the basic bumps and wiggles of a supernova after you could smooth the spectrum. And once I think we were able to show this, it helped people believe that you could actually get a recognition. Now it also helped that the larger telescopes came online just at this time. For example, there's the Keck telescopes that were being developed as I was a graduate student just in the floor above me. I hadn't realized I was going to be using them, and within just a few years, these were the telescopes that we needed to do this kind of work. Now there's another problem that you can see with these spectra that came up, which is that the spectrum of a low redshift supernova gets shifted to the right on this graph, so it looks like this when you get out to these very distant supernovae. That's what we mean by redshift. And most of the light comes through in the blue part of the spectrum, and so typically at low redshift, people study the supernova using the B filter, as it's called. That's what the shape of the filter is that you use to study the supernova, which is very reasonable. But at high redshift, that same blue filter is just looking at this very little, this tail of the spectrum. And there's the question of how are you going to compare a supernova seen at this part of the spectrum to a supernova that's seen with this part of the spectrum. And it was not clear you could do a good job. And in fact, in a paper in 1990 by Bruno Leibengut, he did a very careful job trying to show what the correction would have to be to account for the difference between looking at this part of the spectrum and looking at this part of the spectrum when you compare the supernova. Now, when we found our first supernova that we really were able to follow and we published, the 1992 supernova, it was at redshift 0.45, and we realized something as we started to work on it, which is that the idea that everybody had been thinking we would do, which is that we have to do what's called a K correction to account for the difference between this part of the spectrum and the part that you'll see here, is actually the wrong way to go about it. What you really want to do is look at the high redshift supernova with a red filter, this R filter, and that means that the same part of the spectrum is coming through that filter at low redshift and this filter at high redshift. And once we had shown that in this paper that Alex Kim and Ariel Gubar and I wrote, we felt more confident that we could actually do a very good control of those K corrections and make a very detailed measurement. Now, the next set of issues had to do with how standard were these supernova, and could you rely on them as a marker of distances? And the original plot I showed you of Pangaea was certainly suggested that might make a good standard. And I should also mention that Bruno Leibengut and Gustav Taman were responsible for really, I think, getting people aware of how consistent the Type 1a supernovae were with each other during the late 80s and into the early 90s. And so I think it's important to mention their names in this context. But another group that was very important in this was David Branch's group in Oklahoma, who were compiling data sets of supernova and starting to see that they could also come up with ways of making them even more standard than just the beginning set looked like that Nino Pangaea was working with. And one good example was this paper by David Branch's students, Vaughn and Miller, and I worked on this paper with them, where the point was made that you could take what looks like a fairly tight clustering on the redshift versus brightness plot, but you could make it even tighter if you could just eliminate the supernova that were red. And you could just go and measure the colors of the supernova, throw out the reddest ones, and that would get rid of the supernova that were dimmed by some dust, because that makes them red just like the sunset looks red, and also get rid of a number of the peculiar supernovae that weren't quite the normal Type 1As. So this meant that you could take the dispersion of brightness that you observe from some 40 or 50% range that was seen in that earlier data set down to something like 30% dispersion if you did the selection based on color. But the interesting point here is that this is only the observed dispersion, and in these papers the point was made that these were not very well measured data sets, and that if that actually the quality of the measurement already could account for most of this 30% dispersion that remained, and that it's possible that the supernova were perfectly good standard candles, and you wouldn't know it given those measurements, that we needed better data. So what happened after this in the early 90s was that the Kalan-Tololo supernova search joined in the game, and this was a key moment for this field. I should particularly mention the names of Mario Amui, Jose Maza, Mark Phillips, and Nick Sunseth, who are leaders in this work, because they were really responsible for setting the next stage. And the data set that they developed of relatively nearby supernova that were just far enough out into the Hubble flow that you could actually measure the distances very well was just a unusual new step in this work. And just by using the exact same cut and color that was used here, you could take the dispersion down to some 18% in brightness just with a better measured data set. So this was actually good enough now to do the work that we needed. There was another whole approach to this that also came in the early 90s that Mark Phillips was responsible for kicking off in this particular generation, and that was to use the time scale of the supernova event, so how rapidly it decayed, so essentially the shape of this light curve, told you how bright it would get to be. And Mark Phillips saw this in the early data, and it looked even better when you used the Kalan-Tololo data. Then Adam Rees, who will speak after me, came up with a more sophisticated statistical analysis of this, and I think he may speak a little bit about this as well. And then we were using another approach of just stretching the time axis, just literally stretching how long you watch the supernova, and you could take what was a range of a beautifully measured Kalan-Tololo supernova that have brighter ones and fainter ones, and just measure how much of a stretch you would need to make these light curves match each other, and that could predict the brightness, and you get these very nice new calibrated light curves out of that data set. So these techniques really brought the field another step forward, and they actually made an even further improvement from the 18% dispersion that I just showed you down to 15%, 12%, depending on which techniques you believed you had available to you. Now, the other point is that the question of how you deal with the dust in a supernova, I mentioned one way, which is to throw out the reddened supernova. Another possibility would be to actually measure how red the supernova was and correct for that. And then there was another possibility for the future at that time, which was to go out to much further redshifts, and you could start differentiating at very high redshifts what dust would do to supernova versus cosmological effects. Now, this is something that Adam then really took to its conclusion, and so I'll leave that for Adam to talk about. Now, Finally, there's the concern that the supernovae aren't guaranteed to stay the same over billions of years. We're looking back very far in time in these studies, and so the worry would be that the supernovae back then are not the same as the supernova today. And so if you're going to compare the brightnesses, it may be meaningless if they're not identical. And we realize that there is a nice route to addressing that had been looked at for low redshift supernova and could also be looked at for high redshift supernova in the future, which was much like that plot I showed you before of breaking up the supernova into the ellipticals and the spirals, where the host galaxies were from. And you could do something similar at high redshift in principle and compare these spiral structure galaxies and the supernova that were found inside of those to the elliptical structure galaxies and the supernova found there. And the reason that that's so useful is because the histories of those different environments are quite different. And if the cosmology you get in these different kinds of environments is the same, then you believe that you're not seeing just a different evolutionary history causing the cosmology effect. So this was something that we could do in the future as well. So by the end of 1994, or mid-1994, we had these answers in hand, but now there was one new question that arose. And that one came up partly when we were looking at that first supernova that we found in 1992. And it was, that one supernova by itself didn't give you a very definitive measurement of anything, but it happened to come out with very, very low measurement of how much slowing there was in the universe of mass. In fact, so low that we started to think about a term that Einstein originally put into his equations called the cosmological constant, which has the effect, and Einstein rejected it originally, but if it were there, it would have the effect of fighting against gravity in this expansion of the universe slowing down. And so we realized that if you got a very, very low value for the slowing, it could be due to a little bit of this cosmological constant fighting against gravity. And then how could you tell which it was, whether there was less mass densities, less slowing of gravity, or perhaps more of this, what they call lambda, cosmological constant. And so the concern was you wouldn't be able to tell those apart. So from a paper that Ariel Gubar and I did, here's a plot of this problem, that you could measure a supernova. At that time it was still hypothetical that we'd find a supernova redshift 0.5, and measure its magnitude and get a strip of possible values, and you wouldn't know whether you were down here at the bottom with little amounts of cosmological constant and small amounts of mass, or large amounts of both. It was not going to be possible to tell them apart. But what we realized was that if you look at a larger range of redshifts, if you go out to much, much further supernova, those that are even as far as a redshift of 1 and beyond, then these lines start to rotate, and you could look at those supernovae all together and begin to narrow in on the intersection region here and be able to figure out which it was, whether it was lambda or mass density, cosmological constant or mass density that you were trying to measure. And we in fact even made these plots of showing that you could tell apart on the same amount of mass density, more cosmological constant or zero cosmological constant, and this happens to be just about where the final answer turned out to be. But of course, we didn't know it at the time, and we assumed that we would end up down here. And as my colleague Brian pointed out to me the other day, we even had a hint at that time that it would be easier to do the project if we were up here, because these are tighter error bars than this bigger allowed range at the value that we thought we would get. But so now we were in a position at the end of 1994 to actually start doing this over and over and over again. And so it became a production job. We wanted to churn out enough of these supernova and make those delicate measurements in multiple colors that you needed to make to be able to eventually get a statistical sample and find out what the answer was to how much the universe was slowing down. And we were by now applying to telescopes all around the world to do this, because we had to use telescopes to follow the supernova with spectroscopy. We were doing that in Hawaii. We were finding them in Cerro Tololo in Chile. We were following the light curves with the Isaac Newton telescope in the Canary Islands and the Wind telescope in Tucson. And it was a pretty dramatic scene during these weeks that we'd be doing these operations. We'd be flying down to Chile and getting one set of data, and then we'd fly back again 3 weeks later. We'd have one team of people in Berkeley analyzing the data that we pulled in over the then fledgling internet. We were just barely able to get the data over in time. And then we'd be flying off. We're sending another team to the Hawaii to get the spectrum, while 2 other teams were at the Canary Islands and Tucson. So it was a real dramatic scene to watch, and by this time the team was more than 2 or 3 people that we had at the beginning. This is much of the team towards the end of this period, and I just point out that these are a really important team of people who made it possible to do this. It was absolutely teamwork, as I mentioned last night in the award ceremony. So you should look carefully at the list of names. And what you started to see were we start building up these histograms of supernova. These are the redshifts at which we're finding them. Every one of these color sections shows another semester that we went out to the telescope and we generate, a half dozen supernova, and then a dozen, and then another 8 or 9, then another dozen. And by the end of '97, we finally had enough in hand that we were able to really start seeing significant results. We even had a first hint of what might be happening in our first very high redshift supernova shown here, which we published in the Nature article in 1998, actually it came out January 1st of '98, and it was already hinting that they were down here at this lower values of mass density, and in fact, it was best fit by having the Fermat cosmological constant in the story. But very quickly thereafter, you were really looking at a significant data set. And now, I'd say 90% of this data lies on the below zero mass line here, meaning that there's definitely a cosmological constant in the story, and that's what shows you that you're talking about a universe that's not on one of these lines. And in fact, so when you start plotting the points that we saw before we did this work, the low redshift ones, and now go out into the far past to see which of these lines we live on, the data points missed them all, and that was the big surprise. That apparently we just don't live on one of those universes. We live on, presumably, one of these universes, a universe that used to slow down, but then's been speeding up for the last half of the life of the universe, and presumably could speed up forever. So, the cartoon picture I showed you before, you didn't end up with either of these. You ended up with something like this, and that was really the surprise. So apparently, we have a universe that's dominated by some new ingredient, some dark energy that can want the universe to accelerate faster and faster. And that is so rare that you come across something that is not part of our current physics model. So I will leave the discussion of the implications of this to Brian in his talk and the surprise of this. But I'll just say that obviously, to us, one of the best kind of outcomes that you could ever get from a project. I feel very lucky that we were able to work on a project like this at all, because here's a project where the possibilities that we thought we could be finding out at the beginning when we began the project were all wonderful. They were just fun questions to be asking about, and whatever we found out would have been great. And instead, we got an answer that was even better than great. It was a surprise, and that's not something you can really wish for very, very often. And so it's just remarkable to be in that lucky position. So let me just finish then and say that it's very appropriate for us to be giving this talk and accepting this award here in China, because some of the very earliest records of human records of supernova are in fact the Chinese court records. And I've a number of times asked for people to translate for me the classical characters. I understand the supernova appears down here after some war discussions up there. It's really an honor to be able to be here and returning to the home of the sort of philosophical questions that we're asking and the sorts of empirical observations of the sky that led to an answer. So let me pass it on to my next colleagues who will ask for some questions first. We'll do the questions at the end. Thank you.
Thank you, Professor Perlmutter. We'll hold all the questions and answers. We'll have a Q&A sessions after all 3 speakers are done with the talks. So our next speaker is Professor Brian Schmidt. Professor Schmidt is a Federation Fellow at the Australian National University's Mars Astronomy Observatory. Professor Schmidt received undergraduate degrees in both physics and astronomy from the University of Arizona, and then began his PhD from Harvard University in 1993. Again, Brian won many, many awards. So again, I'm not going to tell you all about these awards, but just to name a few. Professor Schmidt was awarded the Australian government's inaugural Malcolm McIntosh Award for achievements in physical sciences in year 2000. He was selected Bulletin Magazine's Scientist of the Year 2004. He also won the Australian Academy of Sciences Palsy Medal in year 2001. And then, of course, last night he received a Shaw Prize in Astronomy. So let's welcome Professor Schmidt.
All right, ladies and gentlemen, I'm using my Mac for the first time, so it's going to be interesting to see how this goes. My other computer got stolen last week, so I'm hoping... Adam, what am I doing wrong? Just a second, I just have to get into a different mode. We'll try that. All right. So it is a great honor for me to be able to give this talk this afternoon here at Shaw College. And Saul has covered, I think, the subject fairly thoroughly. He was a little bit of a rat because he gave me his talk beforehand, and he's doubled it since then. So there will be a little bit of repetition, but my talk is going to be coming from a different perspective. It'll be at a slightly lower level, which will be good for some of the audience and less good for others. But it also incorporate the experiences that our team took, which were quite different than Saul. We came from an astronomy perspective, where Saul was really coming from a physical experiment perspective. So I want to start back and look back at the history of cosmology, which I think Saul went through fairly quickly, and so I have a little bit of room here to explain things to the non-cosmologists in the audience. So, we go back to the history of cosmology. The beginnings of cosmology, I always think, started in about 1916, when this man, Vesto Melvin Slipher, took the first spectra of galaxies. And so he took the light of galaxies, spread them out through a prism, and looked at the lines of the elements. So every element, iron, sodium, has a color that it absorbs light at. And that is a fingerprint which we can use to measure how things work in the universe. And so it turns out when he looked at these fingerprints of elements for galaxies, he saw something funny. He saw that the lines were actually stretched from where they normally would be. So the iron line was moved over to the red a little bit. And we call that the Doppler shift. It turns out if objects are moving away or towards you, their light is either shifted to the red or to the blue. And he found a very puzzling thing in 1916. He found that almost every galaxy in the sky was moving away from us. Now this was sort of a cosmic conundrum in 1916. Why would everything in the universe be moving away from us? We thought since the time of Copernicus that we were not in a special place in the universe. Why would we be such an unpopular place in the universe that everything else would be moving away from us? So that was a big problem, and it was solved through technology by Edwin Hubble. Edwin Hubble, like most good astronomers, had access to the largest telescopes of their day, and he had access to more telescope time than anyone else. It is not surprising, therefore, he did the best work. Nonetheless, what he was able to do was to measure distances to galaxies. And in 1929, he showed that the further an object was away, the faster it was moving away from us. And he said that means that the universe is expanding. Now that may not be obvious to everyone in the audience why that would be so. So let me do a little PowerPoint trick and show you why it's so. First, I'm going to actually show you his data so that when you look at our data, as Saul has shown his data, and Adam will show our data, ours actually looks pretty good. This is what Edwin Hubble did, and each one of these dots is a galaxy. This is their distance in what we call parsecs. It's be light years, and this is their velocity in kilometers per second. So the further objects are moving faster away from us, but they're also, as I say, more distant. All right, so when we look at our little model of the universe, I hope, here's a little picture of a toy universe, and what you can see is if I expand the universe by a little bit, like that, and I overlay my expansion, and I look at my reference point up here, every object has moved away from that point. These objects have moved a little bit, these objects have moved a lot. This is the idea of the expanding universe. If you expand the universe, the further away you are, the faster you move away. But interestingly enough, if I overlay by a different point, over here, I see exactly the same thing. We aren't in a special place in the universe. Everyone in the universe sees exactly the same thing, an expanding universe. All right. Now, just like a universe which is expanding, if a universe is expanding, you can wind it backwards. And of course, everything gets closer and closer together in the past. And that sort of naturally implies something like a Big Bang. Something that actually took astronomers a long time to figure out, but it's a fairly natural conclusion. So let's do a little graph of what we expect to happen. Right now, we have two galaxies that are separated by some distance. So this is how far apart they are. This is time now. If I wind things back, if the universe is expanding now, I can draw the line back to when the galaxies were on top of each other. And so that is the time down here of the Big Bang. And so by measuring how fast the universe is expanding now, that tells us how old the universe is. And this is something I did in my thesis. This is my thesis, literally encapsulated on the screen. My PhD supervisor is also Adam's PhD supervisor, Bob Kirshner. And what I had done is I had measured how fast the universe was expanding. This is what I did up to 1993. So I was interested in the expanding universe, and it gave a fundamental quantity of what the universe was doing, how old the universe is. And so if we look at what the answer means, the answer I got was a Hubble constant of 73 kilometers per second per megaparsec. Now that's an astronomer unit, but what it implies here is that the universe was roughly 14 billion years old. And it turns out, I think I got the answer correct, because the current established value of the Hubble constant is 72, 73, 71, depending on who you talk to, with an uncertainty of 4 or 5%. So I'm within the error bars. I think I was probably a little lucky, but we won't go there. My error bars were quite a bit larger. So the question then that goes into cosmology is, so how fast the universe is expanding now tells us how old the universe is. But what happens about gravity? Saul told you gravity slows the universe down. And if the universe slows down, the universe is going to be younger than you otherwise think. So how does that work? Imagine I draw my diagram the same as before, and I have a universe which is not slowing down. It follows that line. If the universe is slowing down due to gravity, then the universe is going to take a different trajectory, and the Big Bang is going to have happened not as long ago in the past. So that's one of the reasons why it's interesting to measure this trajectory of what the universe is doing over time. All right, so of course, if we look towards the future, as Saul showed, just to remind us there, these trajectories have different endings. A universe which is not slowing down expands forever. It's infinite. A universe which slows down very quickly is finite. And so, just as we have the Big Bang here, in this universe, we get the Big Bang backwards, which is the Gnab-Gib. All right. So, this sets a stage for understanding the universe. The slowing down or speeding up of the universe, as we know it's speeding up, tells us many things. It tells us how old the universe is from the Hubble constant. That's how fast the universe is currently expanding. It tells us the ultimate fate of the universe, and it turns out it tells us the shape or weight of the universe. So this may not be obvious to you, but Einstein's equations of general relativity tell you that space may be warped. If the universe is heavy, Then the universe is what we call closed. It bends onto itself. This universe is finite. It is a universe, if you have enough time, if you head out this way, you eventually end up where you're standing again. But you need a lot of time. All right, we have the light universe. This universe bends away from itself. This is what space naturally does when it has nothing in it. It has a shape like a saddle. Triangles in this have funny angles that don't add up to 180 degrees. They actually add up to less than 180 degrees. And finally, we have the just right universe. This is a universe that's perfectly balanced between being heavy and light, where space is flat and behaves almost exactly like you expect it to. And it's also just right because when we were in graduate school, the theorists told us this is the way the universe should be because it's the only way that makes sense. Of course, I thought they were wrong, because theorists often are, but it turns out, as we'll find out, they weren't. All right, so moving on, we get to the point of type 1a supernovae. So the goal is to use type 1a supernovae, as Saul said, to measure this fate of the universe. This is a picture of supernova 1994D taken with the Hubble Space Telescope. So let's talk about type 1a supernovae. Somewhere in China, May 1st, 1006, 1,000 years ago, I was in Shanghai about 3 months ago to celebrate this object. This is the earliest recorded and brightest supernova of a type 1a of mankind. So humankind saw this in 1006. This was a type 1a supernova. It was as bright as the moon was when it was half full, but it was a little point of light, so it would have actually reflected inside your eye. It would have been an amazing sight, much brighter than Venus or anything else you see in the sky. And it was around and visible for several years, and recorded in China and a few other places in Europe, but mainly in China. It turns out this object we know today because we see it in the X-rays, and this is what it looks like 1,000 years later. This image is about the size of the full moon, and there's a picture taken with this Chandra X-ray telescope. All right, so type 1a supernovae, I need to explain how do they happen? I need to explain how the sun works. Our sun will expand and engulf our own Earth in about 4 or 5 billion years, and in doing so, when it expands, it will end up throwing off most of its mass and collapsing down to what we call a white dwarf star. A white dwarf star is a star about the size of the Earth, but the mass of the sun. So it has a density which is about 1,000,000 times more than what normal material has. That does not produce a type 1a supernova. The interesting thing for a type 1a supernova is when you have not one sun, but two. So imagine that our sun was a binary star. In this case, the star gets big, but the other star is even bigger, and so it doesn't get eaten. It remains, and that first star turns into a little white dwarf, and then the second star can throw its material onto it. So that other star can grow, and when that star gets about 1.4 times the mass of our sun, it will explode as a giant atomic bomb, expanding at about 20% of the speed of light and having an energy of 5 billion times that of our sun. They are truly one of the most remarkable events in the universe. So a supernova to an astronomer rises in about 20 days and then fades away into oblivion over several months. And these are our standard or standardizable candles that we use as our measuring sticks of the universe. So the way a type 1a supernova works, and this is a little tricky, so we'll see how we do. A type 1a supernova, when it explodes, turns out these things are made of carbon and oxygen. And so when they explode, the carbon and oxygen, I knew this was going to be tricky. Well, we'll see. This used to work on my other computer just beautifully, but it's more challenging now. One more time. It turns out, initially these things burn very slowly, and they burn things like carbon and oxygen to neon and magnesium, a little bit of sulfur or silicon, and then just a little bit of nickel which turns out nickel is highly radioactive and it has lots of energy. At some point, the burning becomes very fast, and the whole thing, the rest of the thing then burns very hot and produces lots of nickel-56, which then energizes the star and causes it to get this 5 billion times brighter than our sun. So, as a standardizable candle, these things date back to this paper in 1968. This was the first paper that actually showed a Hubble diagram, as we call it, a diagram which plots brightness versus velocity away from us. And this diagram was a start. It had an uncertainty per object of about 100%, but it was the beginning of the field, 1968, by Charlie Cowell, using the data taken in the 30s and 40s and 50s and 60s by Zwicky and Botta and Minkowski. So, as Saul has mentioned, there was a lot of poor data which was refined to get the idea of a standardizable candle. But the really important experiment was done by the Chilenos, the Colantololo, who actually went out and did a survey, much like Saul described, where they took photographic plates, not CCDs, of big hunks of sky at the beginning and the end of every month, and they looked for new objects. And then they could schedule follow-up time to get data which followed the objects in brightness. And what they found was that initially they were very scared because the objects were all over the place. They had different brightnesses. And I remember seeing them in 1991, and they were very despondent, saying, oh geez, our entire life is a waste because type 1a supernovae are not good standard candles. But in 1993, Mark Phillips realized that the shape of the light curve told you how bright they were. That is, objects that had broad light curves were brighter, and objects that had narrow light curves were fainter. And he made a diagram here I'm not going to explain in detail, but it turned out these allowed the objects to be used to a precision of about 10%. To give you an idea of what this looks like, in a more graphical form, this just shows the brightness of an object as a function of its light curve shape. And so you can see as they narrow up, they become fainter in this graph. Adam Rees, who will talk more in detail about this, and Saurabh Jha, both students of Bob Kirshner, made it a real industry of statistically figuring out how to use these objects in a very powerful way, and it also allowed us to use dust. And this is one of the cornerstones of the high redshift experiment, was being able to really use type 1As in a way you could trust. And that was one of the things that Adam brought, which was absolutely essential to our experiment. So you might ask, well, what causes this diversity? Why are the type 1As, why are the type 1A supernovae different when I've just told you they all sort of explode when they are 1.4 times the mass of the sun? Well, maybe that's not true. Maybe the objects that explode are bigger or smaller than 1.4 solar masses. Maybe it's because the objects are older or have a slightly different composition. Maybe it's because the explosions are slightly different between each other. That is, that the explosions have a different mechanism. Maybe it's all of the above, or maybe it's none of the above. The answer is we don't know. And that is one of the problems with type 1A supernovae, is we don't fundamentally understand their physics that well. What we do understand is that they are very good distance indicators used as we do. Right now, we have hundreds of objects, and the average dispersion now is better than 10% when you apply Adams techniques on them. So they are a very powerful empirical indicator. So the type 1A high Z supernova history, I think, started with Zwicky first looking and categorizing type 1A supernovae. The contamination that Saul described, where we had these non-type 1A supernovae, which are massive stars, interspersed with the type 1As. And then the very key results of, seem to have a distance thing here, of being able to find the objects. So the Danish team found their first object in 1988, but of course Sol in 1994 found 7 supernovae, fairly with a lot of effort, but at least it was showed to be doable, and the Chilenos coming up with their 1A sample. And so it's those two things here which really triggered my interest. The Chilenos came up and visited us in the spring of 1994, and at the same time, Sol Perlmutter sent Adam Rees, who was on one of his first telescope missions, I believe, with Bob Kirshner and Pete Chalice, I was a postdoc at the time, to look at supernova 1994G. And to our amazement, it actually was a type 1A at a very high redshift, at an expansion age such that the universe was about 4 billion years old. And so I got to analyze a bit of this, but it made me very excited. Sol could find them, our group, my friends knew how to use them, and it seemed, as a fresh postdoc, a good thing to do. And so thus began a race. We decided that we wanted to look at doing this problem from our supernova side rather than the way Sol was doing things from his sort of experimental physics side of things. And hence, we ended up going head-to-head in competition with Sol in this race to figure out the history of the universe. So both teams actually ended up doing things very similarly in the end. We ended up using lots of Saratololo 4-meter time. Here watching the sky go by actually on one of our nights while we sat around and took data. And just to show you how this all works, here's the High Z team, and these are the people, and I just want to quickly go through them. Nick Sunseth here helped found the team in 1994, and we, with him, brought the Chilenos, who are not shown in this picture, and Chris Smith, who was down in Saratololo at the time. At the same time, we also had 2 people from Europe come online, Bruno and Jason, as well as Bob Kirshner, who brought along with him Peter Garnovich, Adam Rees, of course, who you'll hear more from, Pete Chalice, and Saurabh Jha. John Tonry joined later. We needed his telescope time at the University of Hawaii. Alejandro Cocchiai brought time from Chile. Chris Stubbs was at the University of Washington and coming to Australia frequently. Alex Filipenko brought time from Keck at the University of California, Berkeley. And together we went through and worked hard. And so just to give you some action photos, here's Saurabh Jha looking for supernovae. Here's Peter Garnovich looking for supernovae. And there's John Tonry looking for supernovae. So in November 1997, Adam had been tasked, because we knew he could get things done, and boy did he get things done, to reduce in our big data set. And he emailed me in November 1997 and said, hey, look at this, said nothing else, and just attached a figure. And I looked at the figure, and I said, geez, what has he done wrong? Because the objects were not where we expected them. So, to show you why I was concerned, there's a couple reasons I was concerned. One was a paper that Sol had done saying that he thought that there was no cosmological constant, but with poor precision. But it was sort of in the part of the diagram you expected. But also, I had a very deep personal conviction that the universe should not have a cosmological constant. It was just crazy. And as Sol alluded to earlier, I was refereeing his paper in 1995, where he showed this diagram. And as the referee, it turns out when he first sent it to me, it didn't have this part. This was not on there. It just had this in it. And the referee, who I was, and Sol just found this out, I complained, even if you do what you will, the limits on lambda are not interesting. And that's because if the universe did not have a cosmological constant, these were the 68 percentile confidence intervals, and anything was allowed with 95% confidence. I said, this is crazy. Of course, I wasn't thinking that there actually would be a cosmological constant, because Sol rightly put in his paper this diagram, where it turns out there is no way for it to be any normal model if there really is a cosmological constant, because the error bars sort of get pinched off by various things. And so my bias was shown very strongly in 1995, and I will admit being wrong in what I did there. All right. So in 1998, we produced this diagram along with Saul Perlmutter's group, and this just shows the amount of cosmological constant versus the amount of normal matter. And what I want you to realize is that our two groups here agreed almost identically. And our groups were not known for agreeing on much, in public at least. And so the fact that these two groups agreed on things was remarkable. Now, people have often criticized us saying, well, it was only a couple sigma result. But we had evidence for the universe being flat, and if you accept a flat universe, then it turned out that the evidence was extremely strong at 99.9999% level. And so that evidence of flatness was actually given to us by another experiment called the cosmic microwave background, which I'll just quickly remind us of. Cosmic microwave background is a picture of the early universe, and there were many, many experiments that were able to judge the geometry of the universe with this. In addition, other astronomy experiments using large-scale structure were mapping the universe and taking a census. So it turns out that cosmic microwave background, by looking at the bumps and wiggles in the early universe at the time 100,000 years after the Big Bang, you can judge by the lumpiness of the cosmic microwave background the geometry of space, whether or not the universe is open, flat, or closed, has these geometries I was telling you about earlier. The census of the universe was done in Australia by the 2DF Redshift Survey, as well as something called the Sloan Digital Sky Survey a couple years later in the US. And this essentially weighed the nearby universe. And so this measurement provided, and that was with the Anglo-Australian telescope, provided another constraint on what we were looking at. And so when we looked at the astronomy, the supernova results, which were, as I said, unexpected, and shown in this diagram after being constrained a bit, but then you added the 2DF results, that's the weighing of the universe, and the cosmic microwave background results, which go this direction, you see we have a concordance. We all three agree in this one answer, that the universe is about 75% dark energy. So the goal, which Adam, I think, is going to talk more about, is to understand dark energy. This is considered the U.S., by the physics, biggest questions, with the U.S., Europe, Japan, Australia certainly putting significant effort into understanding the answer. And so the big, and I'll just briefly gloss over the two ideas of what we have. One is simply Einstein's cosmological constant. So Einstein in 1917, when he started looking at the universe, looked and saw that his equations of general relativity had the universe expanding or contracting. And that was bad because at that point the universe looked like it was very stationary. It was not moving at all. And so he put in this term which was tied to space itself, an energy attached to space, which once in 1929 the universe was realized it was expanding, he retracted and called his biggest blunder. In modern term, it sort of tells you what is going on in space when there is nothing there. It's saying space is never really empty. It always has an energy associated with it. But there are other ways that could happen, and one thing is called quintessence. So I was wandering around Japan where I realized that I hadn't realized quintessence had been discovered in Japan. This is near Ueno Park. We look at this. This is a hair and makeup gallery. Now, in the U.S., when I have undergraduates, they often get confused between cosmology and cosmetology. This is cosmetology. The question is whether or not quintessence is cosmetology or cosmology. And quintessence differs from the cosmological constant. The cosmological constant is tied to space itself. Quintessence, on the other hand, changes as space evolves. And that is the big question for us now, is figuring out, does dark energy change, which means it's not tied to space itself, probably tied to some sort of particle field that has existed over time, or is it actually just a fundamental parameter of the universe itself? And that's one of the big questions. And so, on that note, I am going to hand over to Adam who is going to sum up everything and tell us his work, which has been very important in demonstrating that the type 1a supernovae are correct, and about getting a better idea on what this dark energy is. So Adam, I guess I'll let you get introduced.
Thank you, Professor Schmidt. So our next speaker is Professor Adam Rees. Professor Rees is a professor of astronomy and physics at the Johns Hopkins University, and he's also an astronomer at Space Telescope Science Institute. Professor Rees got his bachelor degree from MIT and then his PhD from Harvard University in 1996. He's the youngest Shaw Prize winner ever. Now you may find this not very convincing because it's only the third year of the prize. Since I see mostly students in the audience, I'm sure that you have the chance to beat him. He also won many awards. In year 2000, Time magazine named Dr. Rees one of the 100 innovators of the future, and he's one among the 6 in the sciences. He also won the Warner Prize from the American Astronomical Society and a Towns Prize in Cosmology in year 2005 from UC Berkeley. So let's welcome Dr. Rees.
Now I think it was a mistake to agree with these guys to go last. But I will summarize and say, are there any questions? No. Well, Salt covered basically the story, and Brian covered much of the story from our team standpoint. So I thought, what can I really talk about? So what I am going to talk about is, for the first half of my talk, a sort of personal view of how this looked from my viewpoint. So this is sort of like if you've ever seen a movie about or read a book about a murder, and you see it from 3 different perspectives, and only by the 3rd perspective can you really understand what went on. So I hope that that interpretation will be how you see it from my perspective. And then I will talk about sort of an epilogue to the story, a further experiment that we did the years after the discovery that really helped confirm the reality of what we were seeing. So basically, this is my path to the accelerating universe. So my path really began in 1992. 1992 was the year that I graduated from college. I left MIT and was planning to go to graduate school at Harvard. And at the time that I was starting, as Saul and Brian had both described, but now I'll just review, our expectation of the universe was that it resembled one of these 2 models, the one on the left, the one on the right. These are 2 toy models of the universe that both begin with a big bang, and then they begin to grow in size. Now these are 2-dimensional universes. This is just for pedagogy. And so it's the surface of this disk that tells you what the size of the universe is at any one time. And then the universes grow, they expand. Edwin Hubble showed us that the universe is expanding. And then, depending on how heavy the universe is, depending on how much matter is in the universe, the gravity from the matter retards the expansion. So these universes are slowing down. And if the universe is chock full of matter, if it's very heavy, then the expansion will halt at some point and then begin to contract. And as Brian said, we will end in the reverse of a Big Bang. Or if it's a lightweight universe, it will expand forever. Or the theorist's favorite model was the borderline case between these 2, where there's just enough matter to halt the expansion, but not before about infinite time. So we asymptotically reach the point of maximal size. And so, as Saul described, our best methods for determining this was to observe objects within the universe and use them to track change. Smaller, the light travels towards us, and as Saul described, it is stretched to the red because of the change in size of the universe. So we can measure that change in size, and then when we measure how bright the supernova is, that tells us how far away it is, and by knowing the speed of light, that tells us how long ago that supernova exploded. And so every time we see a supernova, we can place a disk in the past expansion history of the universe, separated in time from the present based on the distance to the supernova, and of the appropriate size based on the redshift. And so in this way, we're mapping out the expansion history of the universe in the past and inferring whether it's been changing rapidly due to strong deceleration or only modestly due to very light deceleration. So this is where things stood in 1992 when I started in this field. So my own path to the accelerating universe sort of had me bouncing back and forth from the East Coast to the West Coast. So after I finished college, I went out to the West Coast for a summer to work at Lawrence Livermore National Labs on the Macho project. Now that's actually where I first met Saul Perlmutter, who was doing some consulting for the Macho project. And then later that same year, I went to Harvard University. I began working with my thesis advisor, Bob Kirshner, on a thesis improving distance measurements to type 1a supernovae. Now Brian was the senior graduate student in the group at the time, and the form of governance of our group was such that the senior graduate student generally taught the junior graduate student how to, for example, observe at the telescope and reduce telescope data. And so I learned a great deal from Brian at that time while I was having fun working on supernovae. So Brian was working on one type of supernova, the type 2s, and I was working on the type 1as. And so, as both of our previous speakers described, although there was reason to believe that type 1a supernovae were good standard candles, that we could measure distances from them, by 1992, that was really the critical time when we realized they were not all the same. In fact, there were some in particular, very extreme supernovae which had been seen, of extreme brightnesses. And so we knew that there was something wrong and that we wouldn't get the distances right if they weren't all exactly the same brightness. In addition, we knew that there was a problem, that sometimes we were seeing the supernovae in dusty galaxies. And when you see a supernova through dust, like you see on this diagram here, the dust scatters or blocks some of the light from the supernova, making it look fainter. And when a supernova looks fainter, it fools you into thinking it's further away. And this would be a problem, except we knew that the kind of dust in these galaxies preferentially scatters blue light more than red light. That is, red light gets through more easily. The light from the supernova is, we say, reddened. And so if we understood the color of the supernova before it was reddened, there was some hope that we could account for the amount of dust. So my thesis, which I did with my advisor, Bob Kirshner, as well as Bill Press, was to develop this statistical machinery to take advantage of some clues in the light curves and in the colors of the supernovae. So Mark Phillips had shown that the supernovae which were fainter declined faster. What we did was to use the entire light curve shape, the entire history of the brightness of the supernova, to actually see that the fainter supernovae rose more quickly, fell more quickly, and to derive a robust way to measure that property from the light curves. We also incorporated the use of color measurements to measure the amount of dust in front of the supernova. We developed, as Brian described, a technique called the multicolor light curve shape technique. And basically, the way this worked was, given a set of well-observed type 1a supernovae, and here is a set here, measuring the expansion rate of the universe, this is from the Calan-Tololo group, you could then take those individual supernovae and distinguish which objects were dim because they were far away which objects were dim because they were intrinsically dim, which objects were dim because they were dimmed by dust. And you had to be able to distinguish which of those or what combination of those was going on to get the most precise distance estimates you could. So the same set of objects, when making those corrections, sharpened up our measure of the expansion rate of the universe today. And this was a very important step in our capability to measure, for example, changes in the expansion rate. Something else I did in my thesis was to begin to collect the next large sample of nearby type 1a supernovae. So as Brian described, we look at the history of the brightness of the supernova over a couple of months. We call that the light curve. And so here's a type 1a supernova caught about a week before maximum. Here's one at maximum, and then it declines. And as I described, it's the rate at which it rises and declines that tells us the intrinsic brightness of the supernova, and the colors which tell us the amount of dust. So in my thesis, I collected about 22 of these nearby supernova light curves, and this, at this point, about doubled the sample of well-observed nearby supernovae. So, as Brian described, at this point, the people we were working with, Brian and I, the Chilenos, and some of the other folks at Harvard, decided to form a team to basically do the same endeavor Saul's team was doing, but from a different viewpoint. We thought the anchor of our measurement would be the fact that the members of our team had measured the nearby supernovae so well, the Chilenos and the people at Harvard who had contributed to this second data set, and also our empirical understanding of the supernovae, which could sharpen them up as distance indicators. So we were sort of chomping at the bit to make our own attempt to make this measurement. But as both speakers described, we were so convinced that we would be measuring the deceleration of the universe. It was right in our goal statement from the beginning. That was our assignment, measure the slowing down of the expansion. And so that's what we set out to do. So it's interesting, looking back, since this is sort of a historical talk, what we were all doing at the point of January 1996, just 2 years before the discovery. And this is easy to do because Saul wrote an article for Sky and Telescope magazine in January of 1996 in which he describes what we were all doing. Well, what we were all thought we were doing was we were weighing the universe with supernovae. We were going to measure how much it was slowing down the expansion, and in so doing, measure the mass of the universe. So Saul points out that his team had collected their first batch of these high redshift type 1a supernovae, about 7 of them, and he points out that another team was getting into the game to find distant supernovae. He mentions Brian Schmidt here and a supernova 1995K, which was the first high redshift supernova that our team found. For a short period of time, it was the highest redshift supernova. We were beating each other about every couple of months at that point to the highest redshift supernova. And then he mentions that I was working on my thesis on accurately correcting for light loss due to dust, which I described previously. But the most amusing part of this article is what he says at the very end: such concerted efforts promise to pin down the universe's deceleration and hence its ultimate fate. So if it hasn't been clear at this point, we were surprised. This was not what we were expecting. We were all sure we were measuring the deceleration of the universe. So moving on, around the fall of 1996, I went to Berkeley. After finishing my degree, I nearly joined Saul's group. I had a very nice postdoc offer from his group, but at the last minute I got an offer of a Miller Fellowship down on campus, and so that's where I went. I began doing observations for the High-Z team at Keck with Alex Filipenko, basically collecting the spectra of the supernovae that Brian and the Chilenos found in Chile. I was developing a few more algorithms, one of which was kind of neat. It told us the age of the supernova when we obtained the spectrum of the supernova right at the time we obtained it, which gave us a clue whether that was a good supernova to follow, whether we had found it early enough or it was already too old and we ought to move on. We also began to convert our first round of images of supernovae into light curves on their way to distances. And I was going back over my notebooks and looking at this process, and gee, I've been spoiled in recent years using the Hubble Space Telescope, which takes exquisite images. This process is much easier. But in the old days, we had some really, really poor images. We would say, in astronomy terms, they were undersampled, which means they were very pixely. Each supernova sat on only a couple of pixels. And so here is where the arrow shows a host galaxy just before the supernova blows up. And then here is that same supernova scene just a few weeks later. And the object of the game was to tease out the little bit of excess light in those pixels resulting from the supernova and measure that well. So by March of 1997, the members of our team had made these first measurements, and we were just, getting our algorithms down, just making sure that, that we could even make this kind of measurement. So our first Hubble diagram, it was good at the low redshift end because this is what we had specialized in, collecting that set. We put the objects in the high redshift end, and here is the bifurcation between decelerating and accelerating. And although it's amusing to note that 5 of the 7 objects were on the accelerating region, we didn't give this any credence at all. I mean, we were just thrilled that they were anywhere on the plot. We were just trying to get our basic technique down, and this was just sort of a preliminary run at demonstrating, we were in the game. Now, things got really serious by the fall of '97. We decided to do a really good job. We actually got new images from the telescopes of the host galaxies before the supernovae blew up to get better subtractions and get very nice light curves. We had observed a few more supernovae at that point as well. So it was the fall of '97, and I had inherited this data set to work on, and I was working on it, and going back over my notebooks, I was trying to find a sort of eureka moment, somewhere where I'd scrawl in the notebook, aha, there is, dark energy or something like that. And there really is nothing quite as clear as that. You have to sort of look through more carefully. And so these are the 2 pages I came across. It was in the fall of '97. I was doing a few tests that would be familiar to Brian and Saul. First, I was seeing how the precision of our distances depended on how early we caught the supernova. They were more precise the earlier we caught the supernova. Then I was determining how the precision of our distances depended on whether we found the supernova in a spiral galaxy or in an elliptical galaxy. These were for mostly nearby supernovae, and that was a very important test to make sure that it didn't matter, that the supernovae were impervious to the type of galaxy in which we found them. And then finally, it was on to measuring the deceleration of the universe and the amount of mass in the universe. And so I did what any self-respecting observational cosmologist would have done at this point in the game. I defined the cosmological constant to be 0, because of course it didn't exist, and I set out to measure the mass density of the universe, which turned out to be a negative number. In this case, it was minus 0.36 plus or minus 0.18. Well, what did that mean? Well, interestingly, right, it meant the computer was telling you all it could tell you. You say the universe is decelerating and it's caused by mass, and you ask how much, and it's saying, well, the best fit is a negative number, which is, a sort of a smart alecky way of saying the universe is actually accelerating. You would need minus that quantity of matter to explain what you were seeing. Well, of course, we knew there was no such thing as negative mass, but the next best thing, which we hauled out a few days later, was the cosmological constant. So in this page on the right, I'm calculating the likelihood that the cosmological constant is positive in our data, that we actually need the cosmological constant. And at the end of the calculation, depending on whether we include a certain supernova or not, the result was somewhere between 99.7 and 99.8% likely to be needed. Now, in our field, we call that 3 sigma, and that's just the limit where you say, this is probably not a fluke, this is probably not bad luck, this is probably something real. Now, it's just the limit, and as Brian described, if we assumed just a little bit more, for example, that the universe was flat, then this became a much stronger, more like 7 sigma, more like 99.9 and about 6 or 7 more 9s. But even without that assumption, at the base level, we had something that looked pretty interesting. So at this point, I began working on a paper and passing to Brian parts of the analysis to check, and the last part that he checked, which he talked about, on January 8th, he was in Australia, I was in Berkeley, he sent me a confirming email with the subject line, well, hello, Lambda. Now, lambda is the symbol for the cosmological constant. This was his way of saying, yes, I see the same result. Of course, there was also a diagram confirming quantitatively the results. So this was truly exciting, but also truly scary. And I went over my email log just to show you within a few days how our team was arguing amongst themselves what to make of this, what to do. And it's very interesting to look at their feelings about this. So I say the team was very excited, but they were very nervous. So Alex Filipenko, who had been closer to me geographically, so he had seen a lot of these results earlier, he was pretty excited. He's also a pretty aggressive person by nature. And so he said, Adam showed me fantastic plots a few days before he left for his wedding. I should say I got married just within about a day of this, so it was a really heady time. He says, our data imply a non-zero cosmological constant. Who knows? This might be the right answer. So Bruno Leibengut from Germany, who is very conservative by nature, he's almost the polar opposite of Alex. He wrote, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer we get. There is no point in writing an article if we are not very sure we are getting the right answer. So he was very concerned. I mean, this is the kind of statement you make that you get labeled for. People will remember, oh, those were the guys who said there was a cosmological constant if it went away. Now, Brian wrote from Australia the next day, or maybe that was the same day. It's unclear to me with the time change, which timestamp I'm using. It is true that the new supernovae say that the cosmological constant is greater than zero. He knew that, of course, because he had verified this himself. But how confident are we in this result? I find it very perplexing. And as Brian has said, he actually was thinking in his mind about Saul's team's previous results, or thought that had not improved, and so he really thought that we were going to be in conflict with them, as well as his own perception of what the universe likely was. At this point, the rest of our team advocated going ahead with publication, but with caution. There was a lot of debate in our team about whether we should announce this very quickly, or whether we should, as we would say, write the War and Peace version of our paper in which we explained everything very clearly. Brian and I's advisor, and this meant a lot to us, that he wrote in terms of what he thought, and wrote, I am worried. In your heart, you know this is wrong, though your head tells you that you don't care. It would be silly to say that we must have a non-zero cosmological constant only to retract it next year. So everybody's really concerned about going out on a limb and saying this. They think they're already looking ahead to what jerks we might look like just next year. Alex Filipenko, he was still gung-ho about it. He says, if we are wrong in the end, then so be it, but at least we ran in the race. And so that was his attitude. I wrote in 2 days after my wedding, on the eve of my honeymoon, as we were just about to leave, to the annoyance of my wife, who thought, oh my God, I married one of these people who was going to be working all the time. And I was trying to say to her, no, this is different. I'm telling you, this is really important. It won't always be like this. I wrote, the results are very surprising, shocking even. I have avoided telling anyone about them because I wanted to do some cross-checks, and I have, and I wanted to get further into writing the results. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers, after all. And start thinking of reasons that the distant supernovae could be dimmer, because of course, the big caveat was if there was some other reason the supernovae were dimmer, then all bets were off. And finally, Nick Sunsef from Chile wrote, I really encourage you to work your butt off on this. We need to be careful and publish good stuff. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. Are you up for it? I have no doubt you can be. And of course, he was right. So the two teams published this result, and even by the end of that year, Science Magazine called this the breakthrough of the year for 1998. People immediately realized how profound it was for the universe to be accelerating, what it would imply, not that there was much matter in the universe, but really that there was this other kind of force, this dark energy or cosmological constant. So, as has been described, but I'll show yet one more time how we see this in a diagram. On this axis is the redshift of the supernovae, and on this axis is their brightness or distance. And the nearby supernovae had measured the expansion rate of the universe today quite well. So here we are in the present. And now I've drawn this diagram in such a way that a freely expanding universe without matter or dark energy would have supernovae falling along a straight line here in the past. And deceleration, as resulting from mass in the universe, would have supernovae falling down here, and depending on how far away from free expansion, would tell us how heavy the universe is. So, to our surprise, the supernovae fell up here. In fact, each of these points is really a collection of about 5 or 6 supernovae averaged together, and of course this was what we were all so surprised about. And yet there was still this worry that in this direction, which represents faintness of the supernovae, that these supernovae were somehow fainter for some other reason. So I show you 2 other models here, one where the universe is always accelerating, or supernovae always look fainter and fainter, or another possibility that the universe is accelerating only now but was decelerating in the past. So at this point in time, this is around 1999 now, we knew that these 2 models, the 2 models I came into grad school thinking, you know, this is the way the universe was, were dead. And instead what we had was a different model, one in which the universe is accelerating in its expansion today, but we believed was decelerating in the past. So why was the universe accelerating? Well, we began to talk about some of the ideas that Brian and Saul talked about, that there might be dark energy or vacuum energy in the universe, that there could be a kind of force field. Brian described quintessence, but a sort of a force field like the one that occurred in the universe shortly after the Big Bang that we call inflation. It could be that we never really did understand gravity, how it operates on long distance scales, or other exotic physics. So at this point we realized, wow, this is really big. And it said that extraordinary claims, and this clearly was getting to be that point, require extraordinary evidence. And we, both teams began to work hard on additional tests, additional checks, things we hadn't even thought of doing in the beginning of the experiment because the bar had been raised considerably to show that we had not made some kind of mistake. And so a sanity check I became very interested in was this one of seeing if we could see the universe's deceleration. So why should the universe be decelerating in the beginning, and why is that important? Well, here's our view of the universe. After the Big Bang, there was a soup of particles, and in that soup of particles, there were slight overdensities and slight underdensities. And the overdensities drew more material to them, and the underdensities sort of pushed material away. And those overdensities became the seeds of the clusters of galaxies, and all the things in the galaxies which formed. Now that process will only occur if attraction is the dominant mode. That is, if the universe is decelerating and that the pull of matter is greater than the push of any kind of dark energy that is in the universe, if that is the dominant process in the early universe. And so, because we can see the structures around us, we could see the galaxies had formed, the clusters, the stars, we knew that that process had been dominant in the early universe. The question was, could we actually see that with the supernovae? Now, what was so important about this test is this was a case where we knew what the right answer had to be. There was no doubt. If we failed to see the universe decelerating in the beginning, then we knew that our tool itself had failed us or we had been tricked. And so it was an important measurement to make, but one that only the Hubble Space Telescope could measure. So I formed a new team in 2002, the Hubble Higher Z team, to make these distant measurements, to find the most distant supernovae known and to look for evidence of this previous deceleration. And we were awarded about 40 days on the Hubble Space Telescope over the last 5 years, which is a lot of time. And the reason that Hubble is so good at these measurements can be shown here. Here is a distant supernova in its host galaxy. The supernova is the little dot of light on the right and the host galaxy next to it. And here is those same seen from a large ground-based telescope in pretty good conditions. And so the atmosphere blurs the light, but Hubble is above the atmosphere, so we can cleanly separate and measure the brightness of the supernova free from the contamination of the galaxy. And so Hubble is very good at these kinds of measurements. So how do we find the supernovae with the Hubble Space Telescope? It's the same technique that Saul described to find them on the ground, except we did it a little bit differently. The spacing is a little bit longer. We identified a region in the south and a region in the north, and every 45 days, because we don't have to worry about the full moon, we can go on 45-day time intervals, which is better for finding distant supernovae because time dilation slows their process. We subtract and find supernovae with the Hubble Space Telescope, and in the same way, we can find very distant ones. In fact, here, the first one we found at the time was one of the most distant ever seen, this one at a redshift of 1.3. Here it is seen with the Hubble Space Telescope. Here it is in a color image. Then we turn the near-infrared camera of Hubble onto it and measure it in the rest frame optical light. Then we turn Hubble's prism, slitless combination of a prism and a diffraction grating to disperse the light and measure spectrum. And lo and behold, we collected a spectrum in black that matched a type 1a supernova at a redshift of 1.3. That's the thing shown in red. So once we convinced ourselves we could find these, we were off to the races, finding many of them. Oh yeah, here's the light curve that we caught about a week before maximum and then declining after that. So here are a couple of nice color images. I was saying how much nicer these are from the Hubble than from the ground, where you could see the galaxy and the supernova so well. Here are the after images, and here are the before the supernova exploded images. So after about 4 years doing this project, we have found about 50 of these type 1a supernovae, about 25 beyond the reach of the ground, ones that should have been at the time the universe was decelerating before it began accelerating. So here's the measurement that I showed you before. Here's the acceleration, and the question was, what happened as you went further back in time? And the measurement that we saw from Hubble was very nice. It confirmed that, yes, indeed, we saw what we expected, the deceleration before the acceleration, but that in the most straightforward interpretation, we were not seeing some constant dimming. There was not some astrophysical effect, some grayer kind of dust that lived between galaxies, or that supernovae were just born fainter and fainter as you go back in time. Rather, the supernovae began to grow relatively brighter again, just as we expected, and it gave us further confidence in our ability to use the type 1a supernovae for these kinds of measurements. So what do we know about the dark energy? Very little at this point. We know it accelerates the expansion of the universe. We know it's most of the universe. In fact, there are many other experiments that have now confirmed this same picture, and that was, in fact, the breakthrough of the year in 2003 for Science Magazine. We know the parts of the pie chart of the universe, and that dark energy is this biggest slice. We know it will determine the fate of the universe because right now it dominates the dynamics of the universe, and until we understand it more deeply, we won't be able to make any more predictions about the fate of the universe. We don't know what it is, and right now it's a sort of cottage industry in theoretical physics to come up with models of what the dark energy might be. So at this point, experimentally, the game is switched to trying to characterize the nature of the dark energy so that we can assist the theoreticians as they try to understand what the dark energy is. And so when we think about dark energy, we think of it in a particular way. You might think of it sort of in this way. This was a cartoon from Time Magazine where dark matter acts like a giant rubber band slowing the expansion of the universe, and dark energy acts like a giant spring pushing the universe apart. And that's a nice way to think of it, but it's not the way physicists think of it. The way physicists think of it is in terms of general relativity. And in general relativity, we know that the gravitational force of any kind of medium depends on its mass or energy density right? That part is familiar to Newton, at least. The mass density determines the gravity. What is new from Einstein is that energy gravitates as well as mass, and that internal pressure is another kind of energy. And so there's another contribution to the gravity that comes from the internal pressure. And so different kinds of materials will have different gravity. They will gravitate differently depending on the ratio of the pressure to the energy density, something that we call the equation of state. So for radiation, the internal pressure, which is positive, adds a little more gravity than even its energy does. And so, as demonstrated by the potential energy, it's very attractive for radiation. For matter, it's weaker, but of course still attractive. What we are dealing with now, when we talk about dark energy, the thing that accelerates the expansion, is something where the pressure itself is negative. In fact, it's so negative that it overwhelms the positive energy density, and the sum total is negative. It's repulsive gravity. And so that's illustrated here by potential energies, which are inflected in the opposite way. We don't know if it's a weak kind of dark energy, maybe like quintessence could be, or if it's the strong form, the cosmological constant itself, which is about as strong as it can be. And so our goal is to measure the equation of state and help diagnose what kind of dark energy we have, or at least help the theorists as they predict different possibilities for what the dark energy is. Now, a number of ground-based experiments are working on this right now, and the constraints are improving. But ultimately, we may need to go back to space in a dedicated way. And so the future, really, of dark energy studies is JDEM, the Joint Dark Energy Mission. It's a collaboration between NASA and the Department of Energy joining together to build a dedicated, sort of like a Hubble Space Telescope, but that spends all of its time and is actually optimized to measure dark energy. So another exciting improvement has been a development of a couple of new methods to measure dark energy. I don't have time to get into those, but those are exciting as well. At this point, the interagency approach looks interesting. They've had already one round of competitions. There are at least 3 finalists which have been selected. They expect to have an ultimate selection of the JDEM mission and a launch around 2015, and then I think we could expect results from that probably about 5 years after that. And hopefully, if we're lucky, we may have some definitive answers about the nature of dark energy. And I will end there. Thank you.
Thank you very much. May I call upon all 3 speakers to come up on stage for a Q&A session.